The first set of experiments we're going to look at involves heat being added to a substance. The first experiment we're going to look at is the way that temperature changes as we add heat for a given sample. So for a given sample of substance, this relationship shows a direct proportionality between temperature and heat added. We'll abbreviate heat added as Q, and what we are really concerned with is the effect that Q has on the change in temperature. So for a given amount of heat added, the difference between our starting and ending point here, we have a given change in temperature. If we're moving rightwards, we're heating it, adding heat. If we're moving leftwards, we're removing heat. But we have the same proportionality because that line has a constant slope. That's what makes it a line. So we can say outright that Q is proportional to the temperature change, delta T. So now we know that the line, because it's a line, has a constant slope, and we can think about what that slope might be related to, and we can do experiments to figure it out so we can change our proportional sign to an equal sign. The first thing that would make sense is it would take a lot more heat to raise the temperature of a large sample than a small sample, so we expect mass to come into play here, and we do the experiment and we find out that it does. The more mass you have, the more heat you have to add for a given temperature change. So our ratio Q to M is going to be proportional to delta T. Larger masses, smaller delta T's, smaller masses, larger delta T's. And historically, we move that to the other side of the equation, and this should begin to look fairly familiar to some of you, although not all of you perhaps. So Q is proportional to M delta T. And then we think about maybe the substance matters. So we start doing experiments with different substances, and we find that some substances do indeed require more energy than others. But we also discover that many samples of the same material all have the same behavior. So we assign a constant to that is a property of the material, and it's called the specific heat, and it's related to a lot of internal properties, but of course they didn't know that. They just abbreviated specific heat as C. Times the change in temperature. So our overall result is that Q is equal to MC delta T. To summarize the previous slide, for a given amount of heat, the temperature change depends on the amount of material, the mass, the type of material, the specific heat, C, the phase of the material, solid, liquids, and gases, of the same material have different specific heats, so different values for the constant C, although within each of those phases the constant C is constant. For a given amount of material with no changes in phase, the heat added and the temperature change are directly proportional with our linear relationship. And that is emphasized here. Q is the heat added, M is the mass of the sample, C is the specific heat of the substance in the phase that it's in, so liquid, solid, gas, phase, specific heat. And there's actually two types of specific heats for gases. We're not going to worry about that until a later chapter, but it is something you should be aware of when you look at tables of specific heats. One is at constant pressure, the other at constant volume. And lastly, the thing we're discussing, the change in temperature, delta T. Here is a copy of the table that is in your textbook. And I just want to point out some interesting things here. These values are for constant pressure and a temperature at 20 degrees Celsius unless otherwise noted. So for example, the ice value has a different temperature given. A couple of things I want to highlight here. Water in calories per gram degree Celsius is 1, and that's definitional. That's actually how the calorie is defined. The calorie is the amount of heat that causes a temperature change of 1 degree Celsius in 1 gram of material. And the unit that we will be using mostly, joules per kilogram degree Celsius, that is 4,190 joules per kilogram degree Celsius. So notice that the specific heat for water is actually fairly large compared to most of the substances on this list, significantly higher than the metals, for example, significantly higher even than ethyl alcohol or other liquids that we think of as being somewhat related. The specific heat of liquid water is roughly double the specific heat for ice or steam. And water is fairly high. Liquid sodium has a higher specific heat, but it's not on this list, and it's also explosive. But for some applications, liquid sodium makes a wonderful coolant. And that's really what this list is giving you, is how capable the material is of absorbing heat. So water absorbs a tremendous amount of heat for a small temperature change, whereas something like steel takes a much smaller amount of heat to raise its temperature.